A useful exercise in our analysis of the symmetry of molecules is to construct a group multiplication table once we've identified a point group for a molecule. What I want to use as an example to illustrate this is the point group for formaldehyde. Now I've drawn formaldehyde on here in the plane of the page, which I've labeled as the sigma v prime plane from the symmetry. We've got formaldehyde with this carbonyl axis located along the z-axis, and that is the C2 axis for this molecule. It's a C2 rotation axis. There's another sigma v plane which runs perpendicular to the page, and it contains the x-axis here, and it bisects the molecule into two halves. It runs through the carbon-oxygen bond but splits the two carbon-hydrogen bonds. So this particular point group is the C2V point group. By the way, it's the same point group that water and hydrogen sulfide and other molecules have. And what we want to do is analyze how these various symmetry operations combine with one another, and then their product producing other members of the same point group. So let's look at each of these particular operations that belong to the point group and what effect they would have on a general vector x, y, z. Well, we know that when the identity operator operates on anything, it just gives the same thing back, x, y, z. The C2 operator, in this particular case, operating on x, y, and z, is going to do the following. C2 is a rotation about the z-axis, so it cannot change the z-coordinate. However, it will change the sign of both the x and the y coordinate because it is only a rotation halfway around. So we'll have negative x, negative y, and z as the result of that operation. For the sigma v operation, okay, sigma v is the xz plane, so the effect that it will have on a vector xyz will be to reverse the sign of the y-coordinate, but the x-coordinate and the z-coordinate will remain the same. Finally, the sigma v prime operator operating on x, y, z, this one's in the yz plane as drawn here. And so this one is going to reverse the sign of the x-coordinate but leave the y and the z-coordinates unchanged. All right, so this is going to be the cumulative effect of each of these operations that belong to the C2V point group on these elements. So what we want to do now is construct a group multiplication table that tells us how successive operations for each of these what they would result in and whether it belongs to the group or not. All right, so the way I'm going to construct this, I'll put the name of the group here, and we'll list various operations out here to the right. When you do this, you need to include all of the operations present in a group. And in this case, there's a small number, so it's easy to do. But we normally start with the identity operator as the first one listed there, and we're going to list the same operations down in a column here below the label of the group, the point group. All right, the next operation that we'll include is the C2 operation. Since it's only since n is equal to 2 in this case, there's only one operation related to that rotation. Then we'll have the sigma v operation and the sigma v prime operation. And I'll put them in the same order as we move downward here. All right, so the way we're going to work is we're going to use this operation to operate on the vector first, followed by this. So this is first, and this is second. All right, now the first thing I'll note is that whenever we combine the identity operation with something else, we're just going to get the something else. It's basically multiplied by 1. So when you multiply by 1 twice, you still get 1. So the pair of identity operations is just going to yield an identity operation. And similarly, we can simply copy these operations straight down because they are not altered at all by the operation of the identity operator. It doesn't matter which order we have the identity operator there, it will have that same null result. So we'll end up with these operations as well, and that should have been a prime. All right, so this part of the table, that's pretty easy to figure out. All right, now I'll note that for each of these operations, if I were to operate twice on x, y, and z with C2, the first operation would change the sign of x and y, leaving z unchanged. A second operation of C2 would change the sign of x and y back, leaving z unchanged. So in other words, C2 minus 1 is equal to C2. Or another way of saying this is that the square of the operation of C2 is simply equal to the identity operation. All right, so C2 undoes itself, so it is its own identity operator, its own inverse. So two successive operations of C2 will yield the identity operator. The same would be true for sigma v. All right, the only thing it does is change the sign of the y-coordinate. If I operate it twice, it changes the sign once, then changes the sign again. So it too, if applied twice, is going to give the identity operator. So this is two successive operations of that operator. All right, same will be true for sigma v prime. All right, so we'll have all of these will serve as their own inverse. And that means then that we only have a few of these operations left to determine, and I'll mark those here specially. We need to determine this combination of operations, this combination, and this combination, and then we'll see that these are going to be related to the other three as well. So in this first case, I've got C2 operating first, then sigma v. So I'm basically performing this kind of operation on my vector x, y, z. Okay, well C2 has the effect of changing the signs of x and y. So I'll still have this sigma v. I will have changed the sign of x and y. And now the sigma v effect is to simply change the sign of y. So then I would end up with negative x, y, and z. But we can see that that is in fact exactly the outcome that we get when we operate on it with sigma v prime. So in fact this is equivalent to sigma v prime. All right, if I were to reverse this order, let's say I did sigma v first and then did C2. The result of sigma v would be to change the y-coordinate as denoted here. So I'll have C2 with x minus y and z. And then C2, the operation is to change the sign of x and y. So I'll have negative x, y, and z. And we can see, in fact, that we got the same result as before. So in other words, these two operators commute with one another. Or chances are we've got an abelian group here. All right, so this tells me that, again, I'm going to have sigma v prime as my result. All right, what about if I do C2 and then sigma v prime? C2, sigma v prime second, x, y, z. I'll get sigma v prime operating on negative x, negative y, and z as I did before up here. And the result of sigma v prime is to change the sign of x, so I'll end up with x, negative y, and z. But that's just the same as the sigma v operation. So, in other words, this product of operators gives me sigma v. And I think you should be able to figure out that it will do the same up here, and we'll end up with sigma v. Finally, we have the successive operation of the two sigma v operators. And so I'll have sigma v prime, sigma v, and I probably should have put hats on all of these to make them operators, x, y, and z. Sigma v has the effect of changing the sign of y, so I'll have sigma v prime with x minus y and z. And then sigma v prime has the effect of changing the sign of x, so I'll end up with negative x, negative y, and z. But that's just the operation of C2 on x, y, z. So this will be C2, and again, this will turn out to be C2 also. And so we can see here that Thanks to the abelian property of this particular point group, these two elements are the same, these two elements are the same, and these two elements are the same. They correspond to these operators commuting with one another. So whenever you see this in a group multiplication table, it tells you that the operations here commute with one another and that we have an abelian group. So the other thing that we see here is when we have identity operators along the diagonal, it tells us that all of our elements are self-inverse. So in other words, no matter what the element is, if we apply it twice, we end up with the identity operation. So R is equal to its own inverse. And that's something that we've seen in a couple of groups now. It's not true of all point groups, but it is true of a couple of these examples that we've looked at.